Hello everyone, this is Doc Fan. Very recently, Santa told me he wants to go to the South Pole to meet the cute penguins. But he doesn't want to take cars or airplanes because he's super famous. So he wonders how he can get to the South Pole without the normal transportations. Because the reindeer is on vacation, so he is counting on me to get a new transportation to help him to go from the North Pole to the South Pole. This is a hard question, so I called my friend Isaac. Isaac is a very smart guy. He thought about for 1 minute and then he said, think about the apples. Then he hung up the phone. Alright, I thought about this for a very long time. Then I realized if apples can fall, Santa can fall too. If apple keeps falling until it reaches the ground, how about I dig a hole? If I dig a very deep hole, the apples is gonna keep falling until it reaches the bottom of the hole. So what if I dig a tunnel from the North Pole to the South Pole? Due to the gravity, Santa is gonna fall from the North Pole to the South Pole. Now this is all possible due to the universal of gravitational law, G big M small m divided by r squared. So inside of this tunnel, when Santa is above the center of mass of Earth, the center of mass is pulling Santa. So Santa is basically accelerating, so he becomes faster and faster. But once he is in the lower half of the tunnel, the center of mass is pulling him upwards. So basically, he is decelerating. So now, from the North Pole to the center of mass of Earth, his accelerating velocity becomes larger and larger. But then, from the center of mass to the South Pole, the velocity is decreasing. And the beauty of this motion is from the North Pole to the center of mass of Earth and from the center of mass Earth to the South Pole, these two motions are symmetrical. Therefore, if Santa falls freely with the initial velocity of 0 at the North Pole, he is gonna reach a maximum velocity at the center of mass of Earth, but he's gonna decelerate, so he reaches the South Pole, his velocity will become 0 again. Therefore, this trip is super safe and it is supported by physics. I'm excited about this trip, so I called Santa. Santa really likes this idea, but there is an issue. He wondered how long he needs to stay in this dark tunnel. If it's too long, he will panic. He doesn't want to stay in this tunnel for a very long time. He told me if the traveling time is less than 1 hour, he's gonna do it. If not, I need to come up with a different method of transportation. This really gave me a headache because the force is changing, so the acceleration is also changing. Why? Let's evaluate this situation. So we know the reason Santa is being pulled into the center of mass is due to the universal law of gravitation. So G big M times small m divided by r squared. So when Santa is on the North Pole, the gravitational force equals to G mass of Earth times the mass of Santa divided by radius of Earth squared. Let's call it equation 1. But let's imagine Santa is at this position. His distance to the center of mass of Earth is r. In that situation, the gravitational force will change. Why? Because first of all, the radius changes. Second of all, the mass which is pulling Santa actually only coming from this white sphere. In other words, the mass changes too. So the new force when Santa is at this position equals to G times m prime times the mass of Santa divided by small r squared. Let's call it equation 2. So the mass is changing and the radius is changing. Very likely the gravitational force will change. Then how do we find the time for Santa? if we consider the density of Earth is homogeneous, so the new mass m prime equals to the density of Earth times the new volume, and this volume equals to 4 over 3 pi small r squared. So this is the mass for this white sphere, and this is the real mass pulled in center when he is at this position. And let's call it equation 3. So if we substitute equation 3 into equation 2, let's see what we will get. We get the gravitational force at this position equals to g times rho times 4 over 3 pi r cubed times the mass of center divided by r squared. So this will give us 4 over 3 g rho pi small r times mass. And we know this equals to mass times acceleration, because the gravitational force is the only force being applied onto center. So then we get the acceleration at this position equals to 4 over 3 g rho pi r. Let's call it equation 4. We know if we consider the mass of Earth is me, and if we consider the radius of Earth is re, so the mass of Earth divided by its total volume, which is 4 over 3 pi re cubed, would equals to the density of Earth. Let's call it equation 5. So if I substitute equation 5 into equation 4, let's see what I will get. The equation actually becomes very simple. The acceleration equals to g divided by re times the distance of center to the center of Earth. And this is a very interesting equation. Let's call it equation 6. Because if we consider going up as my positive direction, when center has a distance of r to the center of mass of Earth, this acceleration is going down. So I should add a negative sign here to show the correct direction. This equation is very nice, but there is an issue. As you can see, g is a constant, re is a constant, but r is changing all the time. So that means for this motion, the center has a non-constant acceleration. So you cannot use the normal kinematic equation to find out time. So we definitely need some other methods to find out the time for this trip. I stared at this equation for a very long time, then I realized this looks very similar to a spring block system. Why? Let's look at the situation. For a spring block system, if we consider the net force on the block, the net force equals to mass times acceleration, but it also equals to minus kx. This is the restoring force from the spring, and which equals to the spring constant times the displacement of the spring. And I can get the acceleration for the small block. The acceleration equals to minus k divided by mass times x. This is very similar to the acceleration of a center for this trip, because the acceleration of center equals to minus g divided by re times r. So for the spring block system, this x is the displacement from the equilibrium position. And for center, what we have is this r is distance of center to the center of mass of Earth. In other words, essentially, if a center is going through this tunnel, the gravitational pull of Earth works like a spring. So if center is further away from the center of mass of Earth, you have a large restoring force. But if you are closer, the restoring force becomes smaller. And if Santa is at the center of mass, the restoring force becomes 0. So basically, we can consider the trip of Santa as a spring block system, and we do know the constant here. If you compare these two equations, we can see that minus k over m basically is g over re. In other words, g over re basically is equivalent to k over m. And we know for a spring block system, its period equals to 2 pi times root of m over k. In this case, we know this is k over m. So the period for Santa to travel from North Pole to the South Pole and go back, this is one period, it equals to 2 pi root of re divided by g. So if I consider the polar radius re equals to 6,357 kilometer, and if I consider g equals to 9.8 meter per second square, I got the period equals to 84 minutes. So if Santa is traveling from the North Pole to the South Pole, the time would be half of the period. So the travel time for Santa is about 42 minutes. I called Santa and told him about the time. Santa is super happy. He likes that his trip is supported by solid physics, and he also likes the short trip. Now he told me his plan. Before he's gonna leave the North Pole, he's gonna call Penguin, and then the Penguin is gonna make pizza and hot cocoa for him. And about 42 minutes later, he's gonna arrive at the South Pole. Then he's gonna have fun with the cute little penguins. Since I have helped Santa, he also wants to do a favor to me. He will give gifts to anyone who subscribes to this channel. So if you have not subscribed, subscribe now. Thank you very much. I will see you next time.